Hello, in this video I intend to briefly go over the epsilon delta definition of the limit and demonstrate one problem. Definition. Let f be a function defined on an open interval containing c, except possibly at c, and let L be a real number. The statement the limit of f of x as x approaches c equals L means that for each epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of x minus c is greater than 0 and less than delta, then the absolute value of f of x minus L is less than epsilon. So the scenario is that we have a function f of x that yields outputs in some space between 2 points along the x-axis centered around c, and L is a real number, which is also our limiting value. We are then presented with some notation which you are probably familiar with. The limit of f of x as x approaches c is equal to L. So that limit, that mathematical statement, can be understood via these inequalities. First, what is epsilon? Epsilon is simply a real number that represents the distance between the limiting value L and the endpoints of the open interval centered at L. With that in mind, it's a bit easier to understand the inequality involving epsilon. It means that the function f of x lies inside the interval whose endpoints are L minus epsilon and L plus epsilon. Second, what is delta? Delta is also just a real number that represents the distance between the input value of interest c and the endpoints of the open interval centered at c. So what the inequalities are communicating are the existence of these regions centered around values of interest, namely c and L. Let's look at the definition one more time. Notice that we begin with a given. The given is that epsilon is greater than 0, so there's a region centered around L where there are presumably outputs. If that's the case, then it must be true that there's also a delta greater than 0. So there's a region centered around C where the corresponding inputs for those outputs reside. Put simply, if there's outputs, then it must be true that there's inputs. If we can show that for any epsilon there's a delta, then that communicates the idea that f of x becomes arbitrarily close to L as x approaches c. Now let's do an example. Let's use the epsilon delta definition of limit to prove that the limit as x approaches 2 of 3x minus 2 equals 4. Let's begin with what is called preliminary work, which is essential planning and preparation for the proof that we're about to do. In this case, the purpose of the preliminary work is to establish an appropriate delta value. Begin by writing down the delta inequality. Next, write down the epsilon inequality and unravel it. Recall from the beginning that we established that the absolute value of x minus 2 is less than delta, and working with the epsilon inequality, we arrive at the result that the absolute value of x minus 2 is less than 1/3 of epsilon. So we can begin by assuming that delta is equal to 1/3 of epsilon. And now we may begin the proof. So what we found is a connection between the existence of output values and input values. And because delta and epsilon are arbitrary, we can take epsilon to be as close to 4 as we like. And there will always be an input region around 2 that is 1/3 of epsilon in distance from 2. And with that, we have finished the proof.